We all think about it. The idea of time travel is stuck deep in our minds. What if you could see the dinosaurs? Or meet your great grandparents? What if you could go back and fix that one big mistake? It's a powerful fantasy. It's the engine behind countless books and movies. From a scientist in a DeLorean to a madman in a blue police box, the time traveler is a hero, a trickster, a figure of immense power. But that's all stories. What about reality? Is any of it real? Is time travel scientifically plausible? The answer is complicated. It's a definite yes, a hard no, and a whole lot of weird maybes. It all depends on which direction you want to go. Let's start with the easy part. Is traveling to the future. This isn't just plausible, it's a fact. We know how to do it. You've done it. You are doing it right now. You are traveling into the future at a rate of 1 second per second. That sounds like a joke, but it's the starting point for a much bigger idea. The real question isn't if we can travel to the future, but if we can travel there faster than everyone else. And the answer to that is a resounding yes. The key is a man named Albert Einstein. His theories of relativity completely changed how we see space and time. Before him, we thought of time as a constant, a universal clock that ticked the same for everyone, everywhere. A minute on Earth was a minute on Mars, was a minute on a spaceship flying across the galaxy. And Einstein showed that this is wrong. Time is not constant, it's relative, it can be bent and stretched. It depends on how you're moving. His first big idea was special relativity. It deals with speed. The core concept is something called time dilation. It's a fancy term for a simple but bizarre idea. The faster you move through space, the slower you move through time. This isn't a guess. It's been measured. It's been proven again and again. Imagine you have a twin. You stay on Earth, and your twin gets in a super advanced spaceship that can travel close to the speed of light. The speed of light is the cosmic speed limit, about 186,000 miles per second. Nothing with mass can reach it, but you can get very close. Your twin flies off, zips around the galaxy for a while, and then comes back. For you on Earth, maybe 50 years have passed. You're old now. You've lived a full life. But when your twin steps out of the spaceship, they've only aged a few years. They are still young. From their perspective, everything on the ship was normal. Their watch ticked normally. They made a cup of coffee at a normal speed. But because they were moving so fast relative to you, their clock was ticking much, much slower than yours. They have effectively jumped 50 years into Earth's future. They are a time traveler. This is called the twin paradox. It's not really a paradox, though. It's just how the universe works. This effect isn't just for sci-fi spaceships. It happens all the time, just on a much smaller scale. The GPS satellites in orbit around the Earth are moving very fast. They have incredibly precise clocks on board. And those clocks actually tick a tiny bit slower than clocks on the ground. It's a difference of a few microseconds per day. But if scientists didn't account for this time dilation, your GPS would be off by several miles within a single day. The system would be useless. So, every time you use Google Maps, you are relying on the fact that time travel into the future is real. Astronauts on the International Space Station are also time travelers. They orbit the Earth at about 17,000 miles per hour. Because of that speed, they age slightly slower than we do. When they return after a 6-month mission, they are about 0.005 seconds younger than they would have been if they'd stayed home. It's not much. You wouldn't notice it, but it's real. They have traveled a tiny fraction of a second into the future. So traveling to the future is an engineering problem, not a physics problem. We don't have spaceships that can get close to the speed of light. We don't have the energy sources or the materials, but if we did, we could send someone 1,000 years into the future. The physics allows it completely. But that's not all. Einstein wasn't done. He later developed his theory of general relativity. This one deals with gravity, and it adds another, even stranger way to travel in time. Einstein realized that gravity isn't a force pulling things together. It's a curvature, a warping of space and time itself. Massive objects like planets and stars create a dent in the fabric of space-time like a bowling ball on a trampoline. And just as gravity can bend space, it can also bend time. The rule is simple. The stronger the gravity, the slower time passes. This is also called gravitational time dilation. It means time ticks slightly slower for someone on the ground floor of a skyscraper than for someone on the top floor, because the person on the ground is slightly closer to the center of the Earth's gravity. Again, the effect is microscopic, but with sensitive enough instruments, we can measure it. A clock at sea level will run slower than a clock on a mountain. To see a really dramatic effect, you need a lot of gravity. Something like a black hole. A black hole is an object so massive and dense that its gravity is inescapable. It warps space-time to an extreme degree. If you could hover in a spaceship near the edge of a black hole where gravity is immense, time for you would slow to a crawl compared to everyone back on Earth. The movie Interstellar showed this perfectly. The astronauts land on a planet orbiting a massive black hole. They spend just a few hours on the surface, but because of the intense gravity, when they get back to their ship, 23 years have passed for the crewmate who stayed behind. They travel decades into the future in a matter of hours. The science in that scene is solid. If you could find a planet like that and survive the trip, it would work exactly that way. So if you want to go to the future, you have two options. You can either travel very fast, or you can hang out near a very massive object. The laws of physics are on your side. The future is open for business, at least in theory. But, and this is a very big but, this is not what most people mean when they talk about time travel. They want to go the other way. They want to go back to the past. And this is where things get messy. This is where science moves from proven fact to wild speculation, and where we run into problems so big they might be impossible to solve. The problems are called paradoxes. The most famous one is the grandfather paradox. It's simple. You build a time machine, you go back 60 years, you find your grandfather before he met your grandmother, and you kill him. So if he dies, he never has children, your parent is never born. And if your parent is never born, you are never born. But if you are never born, you couldn't have gone back in time to kill your grandfather in the first place. It's a complete contradiction. The entire chain of events unravels. It makes no logical sense. The universe seems to have a rule against this kind of self-destruction. There are other, more subtle paradoxes too. Take the bootstrap paradox, also known as a causal loop. Imagine you're a big fan of Shakespeare. You get in your time machine with a complete collection of his plays, you travel back to Elizabethan England, find a young William Shakespeare who hasn't written anything famous yet, and you give him the book. He then spends his life copying the plays from the book and publishing them under his own name. They become a huge success. Centuries later, that collection of plays ends up in your hands, and you take it back in time. So, the question is, who wrote the plays? Shakespeare didn't. He just copied them. You didn't. You just brought the book back. The plays seem to have no origin. They are an idea, a piece of information, trapped in a loop forever. And they just exist without ever being created. This violates our understanding of cause and effect. Everything should have a starting point. These paradoxes are the reason most physicists think traveling to the past is impossible. Or causality. The idea that a cause must happen before its effect seems to be a fundamental law of the universe. Going to the past and changing things would shatter that law. It would create a universe of contradictions. But physics is a strange field, and physicists have come up with some very clever, very weird ideas that might, just might, allow for a trip to the past without breaking everything. One idea is called the Novikov Self-Consistency Principle. It was developed by a Russian physicist named Igor Novikov. It's basically the fate solution. The principle states that if you travel to the past, you can't change anything. It's not that some cosmic police force stops you, it's that the laws of physics themselves would conspire to prevent you from creating a paradox. Let's go back to the grandfather paradox. You go back in time to kill your grandfather. You have a gun, you aim, you pull the trigger, but the gun misfires or a bird flies in the way. Or you slip on a banana peel, or the man you thought was your grandfather was actually a stranger who just looked like him. According to this principle, no matter what you do, you will fail to kill him. Your actions in the past are already part of history. In fact, your presence there might even be necessary for history to unfold the way it did. Maybe you go back to save President Kennedy from being assassinated. But in the chaos you create, you accidentally distract a Secret Service agent, which gives the real assassin a clear shot. Your attempt to change the past was actually the cause of the event you were trying to prevent. This view is neat and tidy. It resolves all the paradoxes. But it's also very depressing. It means there is no free will. The past is fixed, the future is fixed, you can be a participant in history, but you can never be its author. You are just a cog in a machine that has already been built, you're just playing out a script that's already written. If that sounds too restrictive, there's another even wilder idea. This one comes from the strange world of quantum mechanics. It's called the many worlds interpretation. This theory suggests that every time a quantum event happens, the universe splits. Every possible outcome of that event happens, but in a separate, parallel universe. Did the electron go left or right? In one universe, it went left. In another, brand new universe that just split off, it went right. This process is happening constantly, an infinite number of times every second, creating an infinite number of parallel universes. How does this help with time travel? It solves the grandfather paradox completely. You go back in time and kill your grandfather, but the moment you arrive in the past and change something, you create a new timeline, a new branch of reality. In this new universe, your grandfather is dead and you will never be born. But that doesn't matter because you're from a different universe. The original one where he lived and you were born. You haven't erased your own history, you've just created a new one and are now stuck in it. This is the solution most often used in modern science fiction. It allows for free will. You can go back and change the past, you can save Kennedy, you can make sure Hitler is never born. But you won't be changing your past. Your original timeline remains untouched, safe from paradox. You would just be creating a new, hopefully better world and abandoning your own. It's a clean solution to the logic problem, but it relies on the existence of an infinite number of parallel universes, which is something we have no way of proving. So we have these theoretical frameworks for how the past might behave. One where you can't change anything, and one where you can, but only by creating a new universe. But these are just ideas about what would happen if you could get there. How would you actually get there? What would a time machine look like? This is where we have to go back to Einstein's general relativity. His equations that describe the warping of space-time are incredibly complex, and buried deep inside them are some very strange possibilities. One of them is the idea of a wormhole, or what Einstein and his colleague Nathan Rosen called an Einstein-Rosen bridge. A wormhole is a theoretical shortcut through space-time. Imagine space-time is a giant sheet of paper. To get from one point to another, you have to travel across the paper. But what if you could bend the paper over and poke a hole through both layers? You could then jump from one point to the other almost instantly. That hole is a wormhole. It connects two different points in space. But since space and time are linked together into space-time, a wormhole could also potentially connect two different points in time. One end of the wormhole could be in your laboratory in the year 2024. The other end could open up in the year 1888. You could just step through. There you go. Time travel to the past. It sounds easy. But the problems are immense. First, according to general relativity, wormholes are ridiculously unstable. The second you try to send anything through one, even a single photon of light, it would collapse in on itself instantly. To hold it open, you would need something called exotic matter. This isn't just matter that's rare or weird. It's matter with properties that we don't think exist. It would need to have negative energy or negative mass. It would have to push space-time apart instead of pulling it together. It would be anti-gravity. We have never observed anything like this. We can create tiny amounts of negative energy in a lab for fractions of a second, but nothing close to the vast quantities needed to stabilize a human-sized wormhole. Second, how would you even make a wormhole? We think they might pop into existence at a subatomic level for tiny fractions of a second, but we have no idea how to grab one and expand it to a usable size. It would require an amount of energy that is far beyond anything our civilization can produce. You'd probably need to harness the power of an entire star. And third, even if you could build and stabilize a wormhole, you couldn't use it to travel to a time before the wormhole was created. You could open one end in your lab today, then take the other end on a spaceship, fly it around at near light speed for a year, and bring it back. Because of time dilation, less time would have passed for the moving end. Maybe only a month. So when you bring it back, one end is in December 2024 and the other is in January 2025. You've created a bridge to the future, but if you keep it running, someone in the year 3000 could use it to travel back to 2024. But they couldn't travel back to 1995 because the machine didn't exist then. It's not a machine for visiting all of history, only for visiting the time since the machine was turned on. There are other, even more speculative ideas for time machines based on general relativity. One is the Tipler cylinder. This is a hypothetical object of immense density and infinite length, spinning on its axis at nearly the speed of light. The math shows that this spinning would drag space-time around with it so intensely that it would create paths that loop back on themselves in time. These are called closed time-like curves. If you flew your spaceship around the cylinder in a specific spiral pattern, you could arrive back at your starting point before you left. But the problems here are even bigger than with wormholes. An infinitely long cylinder? It's a mathematical abstraction, not something you can actually build. The materials would have to be stronger than anything known to science to avoid being ripped apart. It's a fun thought experiment, but not a practical blueprint. Another idea involves cosmic strings. These are theoretical defects in the fabric of space-time left over from the very early universe. They would be incredibly thin, but with an immense gravitational pull. The theory goes that if you could find two of these cosmic strings and fly them past each other at very high speeds, the space-time around them would be warped so severely that time travel to the past might become possible. But again, we have never even detected one cosmic string, let alone found a way to manipulate two of them. It's pure theory. So where does that leave us? Let's take a step back. Traveling to the future is possible. We know it is. Time slows down at high speeds and in strong gravity. The effect is real and measurable. The only barrier is technology. Traveling to the past is a different beast entirely. It seems to be forbidden by the very logic of the universe. The paradoxes of causality are a massive roadblock. And even if we find a way around the paradoxes, like the many worlds or the Novikov Principle, the physical mechanisms required to actually travel back seem impossible. They require things like infinite cylinders or cosmic strings we've never seen, or a type of matter with anti-gravity that probably doesn't exist. There's one final huge hurdle. It's called the second law of thermodynamics. This is one of the most fundamental laws in all of physics. It basically says that in a closed system, things always get more disorderly over time. The technical term is entropy. A hot cup of coffee will always cool down and spread its heat into the room. It will never spontaneously gather heat from the room and become hot again. An egg that you scramble will never unscramble itself. The universe moves from a state of order to a state of disorder. This law is what gives time its arrow. It's why we remember the past but not the future. The past is the state of lower entropy, and the future is the state of higher entropy. Traveling back in time would mean reversing entropy. It would be like watching a broken egg reassemble itself. On a universal scale, this seems impossible. It would violate one of the most well-tested and fundamental principles of reality as we know it. So, is time travel scientifically plausible? For the future, yes. It's just a matter of engineering. For the past, the answer is almost certainly no. While physicists love to play with the equations and see what's theoretically possible, the barriers seem insurmountable. The paradoxes of logic, the need for impossible technologies and exotic matter, and the violation of fundamental laws like the arrow of entropy all point in one direction. The past is gone. It's a country we can remember but never visit. Maybe that's for the best. If we could change the past, would we ever be happy with the present? Or would we be forever tweaking and fixing, creating new problems with every solution until history was an unrecognizable mess? Maybe the universe has locked that door for a reason. Our power lies not in changing what has been, but in choosing what will be. We are all time travelers, after all, moving steadily into the future, and for now, that's the only direction we can go.